You're going to love me and you're going to hate me today. I'll tell you why. So you know all that limit definition of the derivative that we did, that's where the derivative comes from. And truly you can find the derivative that way all day long, right? But the reality of it is that there's got to be an easier way, right? And there's always a shortcut. Now, when we learned multiplication, we learned how to do it the long way. We learned by like making actual groups and, doing all of this hands-on stuff. And then eventually we just learned how to do it just really quick, right? Derivatives are the same way. I made you suffer for 2 days doing the limit definition of the derivative, and you absolutely do have to know how to do that. You need to know it by heart. You need to be able to bust out any moment, because it can be on the AP test. It will be on your tests from now until May. It will be on tests. So you got to know how to do that. However, there's a pattern. And you might have recognized the pattern. You might have seen that there's a pattern in our derivatives. So let's see what that pattern is. And it's a rule that works every time. So remember that we write the derivative in lots of different ways. One of the ways we can write it is d dx, which means the derivative with respect to x, which means x is the independent variable. It's the variable we're taking the derivative of. So we're taking the derivative of y with respect to x. So that's why we write it dy dx. So this means I'm taking the derivative of y with respect to x. Okay, you'll see in a few units why that's more important. Okay, here's our derivative rules. First of all, the power rule. So the power rule says that if I want to take the derivative of some function that has a power, the derivative of that function, of any function that has a power, what I do is I take this power and I move it down in front. So now I have n in front. And then I subtract 1 from the power. So now it's n minus 1. That's it. That's all you do. So if you want to take the derivative of x squared, you bring the 2 down and it becomes 2x. That's the whole thing. That's how you take the derivative of anything with a power. Now it can have more complicated powers. You'll see lots of those in your homework. So what this means is if you think about x cubed, the derivative of that is 3x squared. The derivative of x squared, of 3x squared, would be 6x. The derivative of 6x, well, I bring the power down. I bring 1 down to multiply it by 6. And then I subtract 1 from the power, which is 0. So x to the 0, which is 1. So it's just 6. Do you see how as I take the derivative of a function, I just go to I end up with a function that has 1 lower power than it? So that's just an interesting pattern that you'll see as we do higher order derivatives. The other rule is the constant. So if you have the derivative of a constant, and you guys know this because you saw this in the last unit, you have this constant. I'm trying to find the rate of change of this constant at any given point. Well, is it ever changing? No. Nope, it never changes, right? And because it never changes, then the derivative is 0, because the rate of change of this function is 0. Okay? So the derivative of any constant, any number, is 0. The derivative of a million? 0. The derivative of negative 2.756? 0. All of them. The scalar multiple rule tells us if we have some number multiplied by a function inside the derivative, what we can do is we can actually just take that number, move it outside. We can take the derivative and then multiply the derivative by that number. So if I had something like 2x squared, I could take the 2 outside, not worry about it for a minute. I can take the derivative of x squared, which is 2x, and then I could multiply that by the 2. That's all it says. All right, and the last rule we're going to look at for now is the sum rule. So if I have the derivative of 2 different functions together, so here's a function, and here's a function, and I have the derivative of those 2 functions, then I can just take the derivative of each function separately. So I can take the derivative of f of x and then the derivative of g of x. Let's look at this in practice. See how it actually works. Okay, we're going to differentiate this one. We're going to take the derivative of x to the 4th. So this is the power rule. So I bring this 4 down in front. So it's 4 x, and then I take 1 away, so it's 4 minus 1, which is 4x to the third. So the derivative of x to the fourth is 4x to the third. Remember, this is a function. We get a function out. We put a function in, we get a function out. And this tells us that at any x value we can find the slope of the tangent line. Okay. Next, let's look at this one. So you think, oh, I don't know how to do that. Well, this is two different functions added together. It's this function and this function. So we can just go ahead and separate this. So y prime equals y prime of x to the negative 2/3 plus y prime of 3. So we can take the derivative of both of those. So we can, let's see, the first one's going to be the power rule. So I just bring that power down. I bring negative 2/3 down. Sorry, I'm looking at my handwriting. It's not very good, so I'll try to write better for you. Negative 2/3, we bring it down. We do x, and then we subtract 1 from there. So we do negative 2/3 minus 1. Well, what is that? That's negative 2/3 minus 3/3, so it's negative 5/3. So I have negative 2/3 x to the negative 5/3. And then I ask myself, what is the derivative of 3? Well, it's a constant, so the derivative is 0, so I could put plus 0 there if I really wanted to, but there we go, negative 2/3 x to the negative 5/3. Now this one you start to go like, oh, I know how to do this because I know how to do the exponents, but look, this isn't an exponent. This is like a fraction, right? Yeah, there's some exponents in it, but this needs to be written as just an exponent before we can do anything with it. So we got to get it out of the denominator. You can't just go and start differentiating things in denominators, okay? So we got to look at this, and we can take the derivative of 5. We know how to do that. But this we need to rewrite. So I'm going to rewrite this as 5 minus. Now, if you remember, when a power is in the denominator, to get it up, you can just change it to a negative exponent. A negative exponent, you know, change, cross the line, change the sign. So we go up. That becomes t to the negative 3. So this is 1/2 t to the negative 3. So now that I have that written as an exponent, now I can take the derivative. Well, the derivative of 5 is 0. And then the derivative of this, remember the scalar multiple rule tells me I can leave that 1/2 outside. And I can take the derivative of t to the negative 3. And then I can just multiply the negative 1/2 times the derivative. So the derivative of t to the negative 3, I bring the negative 3 down. So I have negative 3t. Now I take negative 3 minus 1. So this is tricky. It's negative 4 because negative 3 minus 1 is actually negative 4. So pay attention when we have those negative exponents because it's tricky. People always think it's negative 2. It's not. Okay, so then we have negative 1/2 times negative 3, so that's 3/2 t to the negative 4. So that's our final answer on that one. All right, here's another one with a fraction. We cannot just start differentiating this. We absolutely have to get it into a form where it's not in the denominator, right? All of these the variables have to be in the numerator. Okay, so first and foremost, let's go ahead and just multiply out that bottom. So we have 2 to the third, which is 8x cubed. Now this is the same as 5/8 times x to the negative 3. So now I can take the derivative because I've gotten it out of the denominator. So the scalar multiple rule tells me I can keep that here while I take the derivative of x to the negative 3. So I have 5/8, and the derivative of x to the negative 3 is negative 3x. Now negative 3 minus 1 is negative 4. So now I can multiply that together, so I get negative 15 over 8 x to the negative 4th. I could rewrite this as negative 15 over 8x to the negative 4th if I wanted to. I don't have to. In fact, in calculus, this is probably the more preferable way, is just to leave it so that it's just simplified, or not simplified, because you don't want to start messing things up. Because see, actually I did mess this up. Do you see that? I put x to the negative 4th in the denominator. When I put it in the denominator, it changes the sign to positive 4. So this is a great example of what could undo a correct answer on the AP test. If I did this, and then I wrote it like this, I would lose the point because I did not actually, if I wrote it with that negative that I had written incorrectly, I would lose the point. So just make sure that if you simplify, that you simplify properly, but you can leave it, especially on the free response. Now we can take the higher order derivatives. So did you know that the derivative is not the end? In fact, because it's a function, we can just keep taking the derivative of each derivative. So we take the first derivative, that tells us the slope of the tangent line to the original curve, right? Well, then the second derivative tells us the slope of the tangent line to the derivative. You know, so that it's like if I graphed the derivative and then I drew a tangent line, the second derivative tells me the slope of that line, and then the third derivative tells me the slope of the second line. In other words, the third derivative tells me the rate of change of the second derivative, and the second derivative tells me the rate of change of the first derivative. Oh, that's a lot of words, isn't it? So this is our notation, y prime, y double prime, y triple prime, and then it's just, we call it like the fourth derivative. I've never heard anyone call it like y4 prime or anything like that. F prime of x, f double prime, f triple prime, dy dx, and then after this it's just, we say second derivative usually. So there's lots of different notation. Just make sure you recognize every single one of these notations. So if I say find d3y dx to the third, that you understand that that means find the third derivative. Okay, so let's practice a few of those. So here we have a function and we need to find the derivative at 1 and the second derivative at -8. So let's find the derivative. Well, we have to rewrite this. So we have 1/2 and then this is x to the 2/3 in the denominator, because I rewrite that radical as an exponent, because you can't, otherwise we don't know how to take the derivative of it, right? So we always have to write it as an exponent. And so now I want to get that out of the denominator. So this is 1/2 x to the -2/3. So this is just still my function. This is still just f of x. I'm just rewriting it. Now I can find the first derivative, f of x equals, well, I bring the -2/3 down, so I have 1/2 times -2/3 x, and then I subtract 1, so that would be -2/3 minus 3/3, which is -5/3. So the first derivative is -1/3 x to the -5/3. Okay, so that's y prime. Now y double prime is, take the derivative of this function, right? We can just keep taking the derivative of functions as far as we want. So we have -1/3 times -5/3 x, and then we subtract, again, we subtract 1 from that. So -5/3 minus 3/3 is -8/3. So we have 5/9 x to the -8/3. Woo, that's icky, right? Okay. So then we weren't asked to find just the derivatives. We were asked to find what they were at a specific point. So I was asked to find f prime of 1. That means when x equals 1. So guess what? I got to plug 1 into here. So I plug 1 in, and I get -1/3, 1 to the -5/3, which is just -1/3. That's really ugly, but there you go. I had to squish it in there. And then for this one, we're going to plug it in. We're going to get 5/9 x, and x was supposed to be -8 to the -8/3. And guess what? You could simplify that if you wanted. You could figure out what -8 to the -8/3 is, because it's the cube root of 8 to the -8. But why would you do that? We're in calculus. Just leave it. That's it. Don't have to simplify it. I know it's ugly, and I know it's like against everything that you've ever held holy in math, but you can just leave it just like that.